Hi everyone, so this video is going to be also somewhat shorter, hopefully, and it's going to be on the Lebesgue number lemma, which is a result in point set topology that is quite useful in general, and also has some applications in algebraic topology and some places in analysis. So it has to do with coverings of compact metric spaces. And so I've written down the statement, and I'm going to prove it real time. So here we're going to let x comma d be a compact metric space. So x is going to denote the underlying set, d the distance function that induces a metric. And we're going to fix an open cover squiggly u of x. So this is going to be some collection of open sets whose union is all of x. Then, as per the lemma, there exists some positive real number delta, such that for any subset of x with diameter less than delta, it is going to be in some element of squiggly u. In this case, we call delta the Lebesgue number of the metric space xd. So one quick thing is, what do I mean by diameter? Well, if I have a subset of a metric space x, then its diameter is going to be the maximum or the supremum of the distances between these 2 points. So it's going to be the supremum of d of x comma y, where x and y are points in that set, subset of x. Okay, so how do we prove the Lebesgue number lemma? There's some interesting tricks along the way, and it's not too long of a proof in general, so I'm going to start writing it here. Proof. First, we can eliminate one case, which is redundant, and it'll be the case where x is itself part of this open cover. So x is not in this open cover. In this case, any delta greater than 0 is a Lebesgue number for x comma d. Right, and why is this the case? Well, if the whole space is going to be in the open cover, then no matter what diameter of the set is chosen, right, irrespective of this delta, any subset of diameter bounded by that number is going to be contained in an element of this open cover, namely that whole space itself, because every subset is tautologically going to be contained in X. So we can eliminate this edge case, and we can assume that all of these open subsets that form a cover are proper. That is, they're not the whole space itself. Okay, so now because X is compact, it has some open subcover. I should say actually U has an open subcover. Of X. These will be the sets U1 through UN. And these finitely many sets together are going to cover X by compactness. Now let's define, C sub I to be the set complement of these UI in X. Right, because these UI are proper and open, this implies that their complements are going to be non-empty, and because these are open, their complements are also going to be closed. So non-empty plus closed. Okay. So now we have these open sets and we have their complements, which are non-empty enclosed. Now we're going to define this function f, which will be our main tool in proving this lemma. So we're going to define f, which takes points in x to real numbers. In fact, we'll see that the image is actually even smaller than the whole real numbers. We'll prove that as an auxiliary fact. And this is going to take a point to this average 1 over n I equals 1 to n, the average of its distances from any of these closed sets. This is well defined because the C sub I are closed, and we're simply taking 1 over n many sets of these distances, which are just the infima, from the point to this C sub I. Over all I, f is going to represent this average. Okay, claim f of x takes on strictly positive values. That is, it maps into the positive real numbers. Okay. Proof of the claim. Given x in x, choose some element of the open cover such that x is contained in this. This is something that exists because these ui, taken collectively, are going to contain all points of x. And we're going to take some epsilon such that there's an open neighborhood of radius epsilon, an open ball with radius epsilon centered at x, such that it is contained in this u sub I. So this is again possible because these ui are open. So we can take some small epsilon ball about this point that is still contained in this open set. Okay. Now, if we have this epsilon ball that is going to be contained in here, I'm going to try to draw a picture in a second. Actually, let me just write this out here. Now, this tells us that the distance from x to the specific complement ci of ui here is at least epsilon, right? Because equality holds if this epsilon ball is all of ui, and if anything else, if there's a strict containment, then this is going to be an actual sharp inequality. It's going to be a proper bound. So let me try to draw this picture. Let's say this is our whole space X, and we have some open set. Maybe this is, oh, I still have the shape tool on. UI, and then its complement is going to be CI, which is closed. And we're looking at this point X in question. We've chosen this epsilon ball so that this is contained in UI. And notice that the distance from this x to ci has to be at least epsilon, right? The minimum distance from the ci to x has to go through this open ball, and in doing so picks up an epsilon factor in here. It has to be epsilon plus possibly something more, epsilon alone if this open ball happens to touch any part of the UI. Okay, so from this inequality over here and this visual, we can do some manipulation with the sum over here. This gives the following: f of x, where x is that specific point, not just some, it was generically chosen, is going to equal 1 over n times the sum And because this is a sum of non-negative terms, the sum is going to be greater than any of its constituents, or I mean, it's going to be at least as big as any of its constituents. So we can say this is greater than or equal to 1 over n times that specific term x sub ci, that distance from this one particular ci whose complement x is contained in. This is kind of bad notation because I'm using the same thing for an index as a particular set. But anyway, we have this inequality that holds. Because this is going to be greater than or equal to epsilon, we do a substitution, and so obviously this bound is going to get turned into is greater than or equal to epsilon from here and then over n. Right? So f of x greater than or equal to epsilon over n, and x arbitrary proves the claim that it's always positive, because it's going to be at least as big as some positive real number that we pulled out from here. Proves the claim. Cool. So now that we've shown positivity of f, what else can we extract about this function? Well, it's a continuous function on a compact set. X comma d, or I'll just say x. This is going to be extreme value theorem, that it obtains its extrema, or optima, right? It's going to achieve its minimum and maximum value in the real numbers. And specifically what we're going to be interested in is the fact that this implies that it achieves its minimum. And remember, because f is positive, this delta, even though it's the minimum that f achieves, is always going to be guaranteed positive. So this is useful. Okay, so now the last leg of this proof consists of showing that this delta is in fact the Lebesgue number, or a Lebesgue number that works for x comma d. This is the sort of suggestive notation that was chosen here, where delta is this minimum. Now claim delta is our required Lebesgue number. Okay. Proof. Let a comma x be a subset of, I should not do that, of diameter less than delta. Right? And by hypotheses, we want to show that this subset A is going to be contained in some element of the open cover. So choose some x naught in A, right? And no matter what x naught is, no matter how A was chosen, because delta was the minimum value that f takes on, we have that delta is less than or equal to f of x naught, which is less than or equal to the distance of x naught c comma m, this one holding because, equality holds if x naught happens to be the minimum, or happens to be the point such that f achieves its minimum upon evaluation. And this right-hand side inequality, let me define what this is. X naught comma cm is the maximum over all I of distances x0 to c sub I. So there's some index m between 1 and n such that x0 is furthest away from this set, right, this closed set, and this is obviously going to be greater than or equal to f of x0, the image of x0 under f. Okay? So finally, with this pair of inequalities, right, we have our result. And what does this show? Then the delta neighborhood, centered at x0 is contained in u sub m, which is the complement of Cm. And this is because f of x0 is going to be less than or equal to this largest element over here. And so because this delta ball about epsilon is contained in that set, right? Sorry, it's going to be contained in the complement. We have shown that x0 is contained in, let me just be clear with notation. Yeah, it's going to be in u sub m. Since x0 was arbitrary, we have that A is contained in this UM. And we're done because we've shown that this set of diameter that is greater than delta, less than delta, is contained in some element of this open collection. All right, thanks for watching.